Work, energy, and conservation. In a simple pendulum.
A simple pendulum is just a mass or a bob that's suspended from a pivot by a thread. The thread holds the mass up and allows it to swing freely.
So now let's talk about work. In this presentation, I will introduce the formula for work, followed by a unit analysis, and then talk more about how work can be positive, negative, or zero. After that, I'll do a sample problem and then a lab. But wait, before all that, what even is work? Now, we all know that energy cannot be created or destroyed, but it can be converted or transferred into different forms. Work is nothing but that transfer or change in energy, and work is said to be done when a force acts on an object and causes it to move through a certain displacement. For the formula, we're going to be using work equals FAD cos theta, or force times displacement times cos theta. There are a few points here that are worth mentioning, starting with the fact that work is a scalar quantity. This means that it only has magnitude and the sign in front of it does not indicate a direction. This is possible because we're taking the absolute value of the two vector quantities that are here, the force and the displacement. This cancels out their signs so the directions don't reflect onto the work. The force that we use must always be what's causing the displacement in the equation. The theta is always measured between the force and its associated displacement. So if we look at the diagram on the right-hand side, we'll see that the theta is measured between the applied force and the displacement that it's causing. Lastly, work can be expressed on a graph, and I will show you how. For example, if we take the scenario where our super weak friend Linda surprisingly managed to exert 100 newtons of force onto this box to displace it by 20 meters, we could solve for the amount of work done by FA by subbing in the applied force, the displacement, and the angle 0 because the force and its associated displacement are parallel to each other, showing us that the total work done by FA was 2,000 joules. Now we can also graph this scenario using a force displacement graph. Here we can see the 100 newtons of applied force and the 20 meter displacement. So the area under this force displacement graph will give us the amount of work done. And this works because when we use the formula, we're really just multiplying the force and the displacement. And that's essentially the same thing that we're doing when we find the area under the graph. So to find the area of this rectangle, we would just go length times width, or 100 times 20, which would also give us 2,000 joules of work done by FA. Now for the unit analysis, we know that forces are measured in newtons, work in joules, and displacement in meters. If we set up an F net equals ma equation and analyze the units for each of these quantities, we would find that 1 newton is equal to 1 kilogram times meters per second squared, as forces are measured in newtons, mass in kilograms, and acceleration in meters per second squared. If we look at the work equation and do the same thing by analyzing the units, we would see that 1 joule is equal to 1 newton meter, as forces are measured in newtons and displacement in meters. And we found before that 1 newton was just 1 kilogram times meters per second squared. So if we sub that in for a newton, we find that 1 joule is equal to 1 kilogram times meters squared over second squared, which is really just another way that's used to describe a joule. Now work can be positive, negative, or zero, and this is purely dependent on the angle, and that's because in the equation work equals FAD cos theta, we take the absolute value of both the force and the displacement, so the sign can only come from the angle in cos theta. When work is positive, it means that energy is being added to the system. Also, the angle between the force and its associated displacement must be greater than or equal to 0, but less than 90 degrees, or greater than 270 but less than or equal to 360 degrees. This is because all of these values for theta produce positive cos values, which result in positive work. Now, work can be positive in a pendulum if you give it a little push to get it started. So when you do that, you cause an applied force, which causes a displacement in the same direction. And the angle between both of these quantities is 0 since they're parallel to each other. And we know that 0 produces a positive cos value, which makes positive work. And if we take this pendulum that I made, we can actually see this happening. So if I steady this and I give it a little push, we can see that when it first moved, it displaced in the same direction that my hand applied the force in. So the angle between the force and displacement was 0 degrees, making for positive work, which means I added energy to the system, and that makes sense because I pushed it. When work is negative, it means that energy is being removed from the system. Also, the angle between the force and its associated displacement must be greater than 90, but less than 270 degrees. And this is because all of these values of theta yield negative cos values, which result in negative work. Work done by air resistance on a pendulum is negative. Now, if we look at this diagram, we can see that our pendulum is trying to displace to the left, but air resistance is acting oppositely to the right, making the angle between our force and its associated displacement 180 degrees, which we know will produce negative work.
So if we go back to our pendulum and raise it to a height, we can see that with every oscillation, it loses some height and speed, eventually coming to a halt.
This proves to us that energy was removed from the system, so negative work was done by air resistance. Lastly, work can also be zero, meaning there was no change in the system's energy, so no energy was added or removed. Therefore, no work was done. So, how can work be zero? Since we're talking about multiplication here, for work to be zero, one of the numbers involved in the equation has to be zero. So there has to be no force, no displacement caused by that force, or theta has to equal 90 degrees or 270 degrees, making cos theta equal 0. If we look at the picture to our right, we can see that this guy carrying a box is exerting a normal force upward that's perpendicular to the box's displacement. Therefore, the work done by Fn on this box is 0. In addition, the Fn here isn't even what's causing the displacement of the box. In fact, it's not causing any displacement. Therefore, the normal force is doing no work at all. Work done by the force of tension on a pendulum is also 0. Now, if we take any point on the pendulum, let's just say the extreme point, which is the maximum height the bob reaches before it turns around and swings in the other direction, we can see there's the force of tension acting on it from the string it's attached to and the force of gravity. Now let's do something interesting and split up Fg into its components. So if we do that, we can see that Ft and Fg cos theta run along the same line, and so do displacement and Fg sine theta. Since the sine component of Fg is perpendicular to its cos component, the angle between the displacement and the force of tension is also 90 degrees. But wait, is there anything else that's making the work done 0 here? Yes, there is. You see, Ft isn't actually what's causing the displacement. Fg sine theta is really what's making the pendulum move. Ft is just keeping the bob attached to the structure and allowing it to go in the circular path that we see while it's swinging, and that's because of the centripetal force that it causes. Overall, work done by Ft in a pendulum is 0 because the angle between the force and the displacement is 90 degrees, and it's not what's causing the displacement. Okay, I'm gonna need you to turn your brain cells on a little bit for this part. Now suppose we have two pendulums that collide. What do you think would happen to the work done on each bob after this collision? Would it be positive, negative, or 0? To find out, let's take this problem for example, where two identical pendulums with masses of 5 kilograms are dropped from the same height. They collide with an acceleration of 10 meters per second squared, which causes each bob to displace by 3 meters. Let's start by identifying the forces acting on one of the bobs to find the work done. When the second bob hits the first, it causes an applied force and displacement in the same direction, so the theta here is 0 degrees. Now we can use our F net equals ma equation to solve for Fa. Then we can sub all of that into our formula for work to find that 1.50 times 10 to the power of 2 joules of work was done by Fa. And the number is positive, so that means that energy was actually added to our bob during this collision. Now if we take this exact same question, but double one of the masses, how do you think that would affect the work? To find out, let's double our mass. If we repeat what we did before, we can find that Fa has been doubled. And after we put that into the formula for work, we see that work was also doubled, going from 150 joules to 300 joules. So after all of that math, we can finally conclude that mass was proportional to and increased directly with the applied force and work in this case. And I say that because Fa happened to be the only force acting on our bob in the horizontal plane. So now let's get into the lab. I chose one on a ball dropping where I can calculate the Fg for two different scenarios with different dropping heights. And the purpose of this lab is to prove the proportionalities in work equals FAD cos theta. In this lab, acceleration due to gravity was 9.81 meters per second squared because we did it on Earth with the convention down equals positive. Mass was 162 grams. The first dropping height, or final displacement for the first drop, was 2.4 meters and 3.6 meters for the second one. As for the data, I collected the displacement of the ball at different points in intervals of 0.2 meters for both drop 1 and drop 2, the one with the greater displacement. This was done to ensure that the ball was actually going in a straight line instead of curving, and the mass was found to be 0.162 kilograms throughout the lab. Here we have the displacement and force of gravity, or Fg, for drop 1 and drop 2. I used Fg equals mg to find the force of gravity at these points. Here's the force displacement graph for the first drop and the second drop. We can very easily see that these lines are straight and horizontal, but to confirm that, we can find the slope of each graph using the first and last points. After we do that, we can see that each graph has a slope of 0. So these lines are definitely straight. This shows there is a linear relationship between the force and displacement with work. If we use the area under the graphs, we can find the work done by Fg for both of the drops using area equals length times width for these rectangles. After we do that, we can see that 3.8 joules of work was done for drop 1 and 5.7 joules for drop 2. This can also be calculated using the formula for work, and as you can see, we get the same values as we did when we calculated work using the area under the graph. You can also see that work is 1.5 times larger in the second drop, but why is that? Well, it can't be because of the force, because it's the same in both of them. So it has to be because of the displacement. And what do you know? The displacement is also 1.5 times larger in drop 2. So in our lab, when displacement increased by a factor of 1.5, work also increased by the same amount. This would also be true if it was Fg getting multiplied by 1.5. Work would still grow by the same amount. So was the actual proportionality of our physical quantities the same as the theoretical ones? Yes, it was. We show there is a direct linear relationship present between the force of gravity and displacement with work. We proved this using the graphs from our lab and the formula for work. That concludes my presentation on work. I added a lot of energy to it, so this project was some serious positive work. I hope you enjoyed listening to me, but now let's get into conservation of energy.
We're now going to be talking about kinetic energy and conservation of kinetic energy. Now, what is kinetic energy? Kinetic energy is energy of an object that has because of its motion. Kinetic energy of an object depends on both its mass and its velocity, while velocity does play a much greater role. Kinetic energy can also be transferred between objects and even transformed into other kinds of energy. For example, if a ball is thrown at a wall, the kinetic energy will transform into sound or even heat energy. To figure out how to find kinetic energy of an object, you will need the formula Ek equals 1.5 mass times velocity squared. The mass is going to be in kilograms, while velocity is going to stay in meters per second. Kinetic energy depends on the velocity of the object squared. This means when the velocity of the object doubles, its kinetic energy quadruples. Car crash if they go 2 times the speed limit. Let's now start off with deriving the formula of Ek equals 1.5 mass times velocity squared. Now we already know the formula of work, which what Sona talked about, like work equals mass times acceleration times displacement. But we also need to know that work is equal to the change in kinetic energy. We now need another equation from kinematics, which states that the final velocity squared equals to the initial velocity squared plus 2ad. We now need to solve for AD from the second equation. So v2 squared minus v1 squared equals 2ad. Now we need to divide 2 on both sides, and now we get v2 squared minus v1 squared over 2 equals ad. We can now substitute this into the work equation and solve it out. So work is equal to change in kinetic energy. So Ek equals 1.5 mass times v2 squared minus v1 squared. Then we can multiply it out, and then we get Ek equals 1.5 mass times v2 squared minus 1.5 mass times v1 squared. We now have the change in kinetic energy, which equals to the final kinetic energy minus the initial kinetic energy. With that, we can find out that Ek equals 1.5 mass times velocity squared. Let's now do some unit analysis. Remember when we were solving for both the car's kinetic energy? I always said that the unit was in joules. But what is a joule, and why is it in joules? Well, 1 joule is defined as an amount of energy exerted when a force of 1 Newton is applied over a displacement of 1 meter. 1 joule is equivalent of 1 watt of power that is radiated or displayed for 1 second. Another equation for 1 joule is 1 Newton multiplied by 1 meter. We can get the equation Ek equals 1.5 mass times velocity squared. We can get the variables and say kilograms times meters per second square can equal to kilograms meters square over